Hi everyone. We have one last unit here to cover, or one last section, I should say, in Unit 7, having to do with differential equations. And this is specifically dealing with exponential models. So there's definitely going to be some throwback stuff to Algebra 2 here where we talk about what an exponential model does or what an exponential model looks like. Okay. There's actually even, we're going to start out with a throwback to Algebra 1 here. So if you read this first question, it says, what type of function has a rate of change that is directly proportional with the function itself? Sounds like word salad, I know, but let's dissect this a little bit. So this is our Algebra 1 throwback, this concept of being directly proportional. And when we were in Algebra 1, we talked about things being directly proportional if you could like get one value by just multiplying the other value by a constant. Okay, so if you could just do, I'm going to take this and multiply it by 3, or I'm going to take this and multiply it by 5. Basically, there's a constant multiple in there. That's when two things are directly proportional. Now, the way this sentence is structured, it's not y and x that we're making be directly proportional here. We're talking about a rate of change, which in other words, that's a derivative, right? So dy dx, and that's my rate of change, is directly proportional. So that means it's going to be like, there's going to be some constant multiplier. K just represents some number with the function itself. The function, we're talking about the y value, the outcome of the function. And this is kind of a remarkably common situation that comes up in derivative type situations in differential equations. So again, the function itself, that's this y value here. Okay, and you'll see some of this wording and some of the word problems that we talk about too. So kind of important to understand what this is saying. What I'm about to do is prove to you something that will always, always, always happen in this situation. The proof itself is not the critical piece. Okay. The proof itself, I think it's important math for you to understand how to do. I hope you can follow what I'm doing. But at the end of the day, you're not necessarily going to have to do this proof on your own. However, if you got into the middle of one of these problems and got stuck and couldn't remember the theorem that we're trying to prove here, the shortcut for it, you could essentially recreate this process inside whatever problem you're working on. So I definitely try to absorb as much of it as you can, but at the end of the day, we're going to get to a specific relationship here. Essentially, we're going to answer this question: what type of function does this happen in? Um, that that is supposed to make this like a shortcut for you. Okay, so let's suppose that I'm going to come in here and I want to do separation of variables, right? So I'm going to divide by y on the other side. I'm going to move the dx to this side. So I'm multiplying by dx here and multiplying by dx here. I'm dividing by y, and then I'm going to put a 1 over y here. This is going to cancel. This is going to cancel. And so now what I have is, this is separation of variables, by the way, is 1 over y equals k times, oh, I'm sorry, lost the dy there. 1 over y dy equals k dx. And this is where I would want to take an integral on both sides. And I want to remind you that k is a constant. K is just a number. Okay, so my antiderivative of 1 over y is natural log of y. And then over here, this k is going to become a kx. And then we're going to throw in our plus c. So now we need to solve for y. And the way we're going to undo a natural log, this is where our algebra 2 skills are going to come in. Remember, a natural log has a base of e. I'm going to turn this thing around, okay? And I'm going to say that e to the power of this thing is equal to y. So e to the power of kx plus c is equal to y. All right, that's just from properties of a natural log. And then when you have exponents that are being added together, they got that way because we must have multiplied two values together. So don't write this down, but remember, like if you do x squared times x to the third, you would say, oh, well, that's x to the fifth, right? Which is really x to the power of 2 plus 3. So when you multiply two quantities together, you add their exponent. So if I have these exponents that are being added, I can take them back apart by saying this is e to the kx times e to the power of c equals y. And think about putting that back together again. Maybe you wouldn't have thought to do that, but verify for yourself that this would still create this same value. So here's the thing with what we have now. E to the power of c, remember e is also just a number, okay? Um, so e to the power of c is just a constant. It's just another constant. And we can actually take that constant and just put it in front of this e to the kx. And I probably should have used a different letter besides c here. I mean, we're used to using c. I want to make it very clear that what I'm about to put right here is just c. It's not really the same as what this c value would be. This e to the c is just some arbitrary constant, but kind of like what we talked about yesterday when we said, look, we could subtract these two c values and then just rename it c. That's the same idea. So I'm going to just say this is now ce to the kx is equal to y. This is your big takeaway, okay? Is that when you find yourself in this situation, think about where we started with a derivative equal to something times y. You can just jump to this layout. Okay. And again, helpful to understand how I got there because you could recreate that if you had to. But really, what I want you to be able to do is when you see this or when you see wording similar to this, you can just say, oh, I know how to set this up. And I want to point out this K value sometimes will be given to you. Like if you look at some of the examples down here, you'll see that some of them just have the K value in them. So you can just put a number there. And then also this is an exponential function. So this C value is always your initial value. So in other words, this is the value when x is equal to 0. That just goes back to some algebra 2 stuff that whenever you're working with exponential functions, this number in front is your initial value. Because essentially if I put 0 in here, it would cancel all of this out and you'd be left with just c. So that's going to be helpful to you too. Okay, but this is the, like I said, the big takeaway. This is how I got there just with separation of variables. And so now let's check out example 1. So notice that setup, dy dx equals 2y. That's the setup that we're used to. And it says y equals 1 when x equals 0. So let's start. This is technically like an initial condition right here. Okay. That I'll plug in just a second. Let's start by just setting this thing up. Okay. So if dy dx equals 2y, then my solution or my antiderivative, I can just jump straight to saying it's c e to the power of k, and k is my 2 right here. So 2x, okay? And then additionally, I really love when x is equal to 0, because when x is equal to 0, that means this thing right here is my c value. So let me make a note here that this was my k value here. This is my initial value. Okay, now if you don't believe me, what do we do with an initial condition? Usually we plug it in for x and y and we solve, right? So I would put the 0 here and I would put the 1 here. And if you did that, you would find that you're left with just c over here, and c would equal 1. So we can now say that this is really just y equals 1. I don't really need the 1 here, but just making a point. E to the 2x. Okay, that's my solution to this differential equation. And now I can answer this question. What is the value of x when y is equal to 3? So now that I have my function, I want y equal to 3. So I'm going to say 3 equals e to the 2x. Ooh, let's see if we remember how to solve something like that. Again, we've got some algebra 2 skills coming back to haunt us. We've got a variable up in the exponent with an e in the base. So I would solve that by taking a natural log on both sides. You're going to get really good, by the way, in this section at this whole idea of like, to get rid of a natural log, you do e to the power, and to get rid of e to the power, you do a natural log. Those two things reverse each other. When you do this over here on this right side, this 2x is going to slide down in front of your natural log, and then you're just going to have natural log of e, which is 1. So the natural log of e is going to cancel out, and that's going to leave me with natural log of 3 I guess let me write this way so that you can see what I'm talking about. I was trying to be lazy about it, but that's what you're going to be left with. Natural log of 3 equals 2x times natural log of e. But natural log of e is just 1, so that goes away. And then all I'm doing is taking natural log of 3 and dividing by 2. Okay, so let me show that. I'm going to divide by 2, divide by 2. Calculator for this guy, unless we just leave it in terms of natural log, which would be fine. I'm going to say natural log of 3 divided by 2, and I would find that my x value is 0.549. Okay, and that's all there is to that. Okay, let's try a more contextual situation here. So we have a kitten weighs 85 grams at birth. That sounds an awful lot like an initial value. I'm going to just mark this real quick. Okay, if it's at birth, that's initial, right? I'm assuming. I guess I haven't read the rest of the problem yet. During the first 4 weeks after the kitten's birth, its weight in grams given by this function. With this differential equation, look at that setup. Okay, that's what we're used to, right? dw dt equals k times the dependent variable. T is measured in days, k is a positive constant. Which of the following could be an expression of w of t? So in other words, the solution, right? I'm using this thing here. Sorry, I'm pointing stuff you can't see. Using this setup, okay? So my initial value, this is going to be my C value, okay? Because it's my initial value and this is an exponential function that I'm building here. So I can say for sure that my function is going to be W equals my initial, so it's 85, E. Now I don't have an actual K value, right? So I'm just going to leave it as K and then times T. And that's what I know my function would look like. Now, if they gave me another set of measurements, if they gave me like the weight at 3 weeks is such and such, or I'm sorry, the weight at 3 weeks is such and such, and I would put the number here, I could plug in and solve for what K is. I don't really have a way to solve for K, but this is a multiple choice, right? And the question is just which one of these could be it. So let's look at which one of these matches our format, right? If we know this relationship is true, we know it has to be one of these exponential functions, and that 85 is our initial value. So we don't have a way to solve for this 0.059 in this example, but it's the only one that matches this format. So our correct answer here is A. Okay, let's keep going. All right. The rate of increase of a population is proportional to the population size. Let's just write that down real quick. The rate of increase of the population, so that would be dp dt, is proportional. That's where we're going to say k times the population size, which is p. Okay, there's that setup we're so used to. The population doubles every 10 years. So what is the constant of proportionality? Constant of proportionality, by the way, that's asking me to find the k value. Okay, so I'm going to solve for k here in a second. So let's go ahead and convert this to our exponential function. And I don't have a lot of numbers to work with here, at least not yet. So what I can say so far is that p must equal, I don't want to use an equal sign here. Let me use an arrow. C e to the power of k times t. Okay, I know that format is correct. Okay, so this is my initial population, right? And the only information I have to work with is that my population is going to double every 10 years. We did problems like this last year in Algebra 2. So like, for example, and I don't know that you need to write this down. If you think it's helpful, you can. But let's pretend for a second that the initial population was 100. Okay, so I'm going to start my function out as 100 e to the power of k times, and then this is where my t value is going to go. Let's see what would happen in 10 years. So I'm going to put 10 in for t, and I know that my population is supposed to double, so this will be 200. Okay. Well, the very first thing I would do to solve this, sorry, I think I have a blurry spot on my camera there. The very first thing I would do to solve this is divide by the 100. right? I would say let's divide by 100, let's divide by 100. And 200 divided by 100 just leaves me with 2e to the 10k. And that would have happened regardless of what population I chose here, right? Because I made up this 100. But what if I started with 5 people and I changed it to 10 people, right? In 10 years. If this was 5 and this was 10 and I did my division, this would still end up as being a 2. So the fact that my population is doubling, okay, this right here means that when I go to solve this thing, what I'm really going to do is put a 2 in for P, and I'm going to treat this C like it's a 1. I'm turning a 1 into a 2, and that's how I'm doubling. And that is after a period of 10 years. So I'm putting 10 in for T and then solving for K. Don't let that mess you up because I wrote it backwards. The 10 is the T, and then we're solving for K. Okay, let's think about how to solve this now. I have an e to the power of something. So let's take a natural log on each side. And remember, that's going to let me bring my 10k down in front of this thing. So I'll have natural log of 2 equals 10k times natural log of e, which again, natural log of e goes away. And so really the math that I'm doing is just natural log of 2 divided by 10. Okay? Natural log 2 divided by 10. And this is my k value, 0.069. And that's my constant of proportionality, meaning that is the growth factor that exists between that rate of change and the population itself. Okay, so really what we're saying is like, dependent on the actual population, your rate of change is always just going to be a constant multiple of whatever your population is at the time. Okay, and that happens anytime your function is an exponential function, one of these kind of formatted exponential functions, where you have this real direct relationship between your rate of change and the function itself. Okay, one more of these to try. And of course, as always, if you wanted to pause the video and try this one on your own, I definitely recommend that. Um, During a chemical reaction, the rate of change of the amount remaining is proportional to the quantity of the chemical remaining. Okay, so I don't know what we're because I don't want to use C for chemical reaction. So I'm just going to use a Y for the amount of chemical. I'm just going to call this Y. So I'm going to say dy dt, okay, proportional to the quantity of the chemical remaining, so ky, okay? When the reaction begins, ooh, that's good news. When it begins, the amount of the chemical is 12 moles. That's an initial value. I want to write this. And remember, your initial value is your C, okay? So when I go to convert this into our solution equation, I'm going to say y equals, my C value is the 12, E, I don't know what K is yet, so I'm just going to say K times T. Now, it gives me one set of numbers, right? It tells me that at time 4, there's 4 moles of this chemical. So this is your T and this is your Y. So I'm going to plug those two in to solve for what my K value would be, okay? So when time is 4, my chemical is 4, okay, everything is 4. So 4 equals 12 e to the power of, my T is 4, so 4K. I would probably start here by dividing by the 12. So 1/3 equals e to the 4K. 4K. Natural log on both sides. And I'm going to start kind of taking a shortcut here. Over here on this side, I know that looks like a little bit of a mess. But now what I'll just have is natural log of 1/3 equals 4K, because the natural log got rid of my e for me. Let's divide by 4. Okay. And natural log of 1/3, natural log of 1/3, close your parentheses, and then divide by 4. This is my K value, negative 0.274. So I want you to watch something. On my paper, I'm going to write down this number two 3 decimal places, which is our norm. Okay. Whoops. Okay. Oh, put a 0 in there. Sorry, I was distracted by my screen turning off. Negative 0.275. However, I don't actually want to use that shortened decimal when I do my calculation, because in a second, I'm going to do the actual calculation that the question's asking me. At what time is the amount equal to 3 moles? I want to use this entire number that's in my calculator. I want to keep this entire decimal intact. Okay. There's a couple of ways to do that. I think for the sake of this video, I'm just going to keep this number here and then use the answer button when I do my next calculation with it. But really important to try to maintain that entire decimal if you can. Okay. So now I'm going to start over. I'm going to start with y equals 12e, and I know my k value right now, negative 0.275 t. And now I want to plug in the 3 for the y. So 3 equals 12e to the negative 0.275 t. Well, let's divide by 12, so we get 1/4 equals e to the negative 0.275 t. I'm going to do a natural log on each side again. So natural log of 1/4 equals negative 0.275 t, because my e went away. And my next step here is where I want to divide by the negative 0.275. So watch how I'm doing this in the calculator. Natural log of 1/4 divided by, and then to keep the entire decimal, I'm going to just use the A and S key. And I end up with 5.047 as my t value. Let's just see. So college board standards are you have to have 3 decimal places correct. Okay, your decimal has to be correct to 3 places. So if I had done natural log of 1/4 and then just divided by negative 0.275, which was the decimal I wrote down, look at what happens. I get 5.041, which is not technically correct, right? It's off by a decimal place. So when you're going to be using a number later in your problem, it's really important to try to maintain that entire decimal in there. And I do think that there's some other shortcuts I can show you with the calculator that we'll make sure to talk about in class. But for now, whenever you can, I would just keep the number in your calculator and then use the ANS button to make sure you're using the entire value. Okay. And this should make sense to you because this thing is, let's see, it's decaying, right? Because we found that our K value is negative, so it's decreasing. It's a negative rate of change here. Um, and so at 4 minutes, we have 4 moles of the chemical left. So for 3 moles, that we're going to go a little longer, right? And so at 5.047 minutes, that's when I would have 3 left. So that should make sense to you, hopefully on kind of a practical level. Like I said, if you did not know this shortcut, essentially what you would do with every one of these problems is that process I did at the beginning, where you would do a separation of variables over here, and then you would plug in your initial value and find C, and then you would, plug in the values that you're actually looking for. It just makes your process longer. So knowing this relationship is a good time saver for you.